That's it. Good. Okay. Well, thank you very much. Thanks, Finn, and thanks everyone for this opportunity to present to the Mot4Rivers project to you. So I'm Andrew Tyler. I'm from the University of Stirling, and I also play a key role here with the Scottish water sector and funded by Scottish Water, fundamentally to help deliver on its net zero ambitions by 2040. And the programme is a £3.5 million programme funded through the Scottish Funding Council, to really bring the research innovation community together to help deliver on that ambition. And that includes challenges around the circular economy, reducing and cutting process emissions, thinking about embodied carbon, but also fundamentally enhancing the natural environment. And this call sits very squarely within that particular mission. And as a demonstration, what we've done is pull together an extensive team to provide that interdisciplinary response to the particular missions of this specific call. So Mot4Rivers then is about monitoring, modelling and mitigating pollution impacts in a changing world, and it's delivering the science and tools fundamentally for us to manage tomorrow's rivers. So it is a consortium. It's led by Stirling, but includes University of Glasgow and Edinburgh. I noticed Edinburgh is missing on the introductory slide. UK Centre of Ecology and Hydrology Institute, the James Hutton Institute as well, and Scottish Water is a key partner on this and a key enabler for this project in particular. So our starting point then for this project recognises, that there is a complex jurisdiction of bodies responsible for water management, but that results in data and indeed intelligence on water being fragmented or even siloed in time and space and across organizations. And often those data sets are also incomplete. Indeed, those data sets are really focused on understanding status rather than process. So this fragmentation fundamentally hinders our understanding of that continuum, that water continuum, and how freshwater ecosystems are responding to multiple and complex interactions with different stressors. So our ambition here is then to transform this status quo by bringing together the key partners and players, building on existing research and innovation programs, which I'll touch on later, and ultimately implement state-of-the-art science and technologies to help us grow that intelligence on the hydroclimatic controls and the fate and impact of pollutant cocktails, and that increasingly complex cocktail of pollutants that are impacting on our aquatic ecosystems, and understand and grow that understanding on the differential sensitivity of our ecological communities and their structure and function to these stresses, and also provide as decision support tools for testing interventions for the mitigation and adaptation into the future for the benefit of us, our freshwater environments. So we have broken down our program into 3 work packages. That sort of stakeholder engagement, that co-development is core to these work packages. So we don't have a separate work package for that, but we are working with both sort of the regulatory community, the industry, and the water utilities, but also with communities as well. So we're working at that local scale in terms of stakeholder engagement as well as at the national scale. And so we have these sort of 3 work packages then that really focus on understanding high resolution events. And that's work package 1, where we are building a digital observatory at the catchment scale that will enable us to understand those high resolution event-based impacts of climate extremes and their interactions with pollutants, so that we can understand that acute ecosystem exposure. And that contributes to the call's theme 1 and 2 in particular. Work package 2 moves from the catchment scale to the national scale, combines national scale data sets to improve our understanding of the long-term chronic exposure of contaminants on ecosystems across sort of climatic and geographical gradients. And that again also meets in particular sort of themes 1 and 2 of the call. And then building on work packages 1 and 2, work package 3 will exploit sort of a probabilistic framework to explore the ecological safe space, which I'll describe that we've just described, and this will then deliver that sort of decision support tool to support the implementation of strategies for pollution mitigation. So theme 1 then will be tackled by the work packages 1 and 2. So for work package 1, we focus on one of Scotland's most polluted rivers, the Almond catchment, which at times is characterised by between 60 and 70% of its water is coming from wastewater treatment works and discharges from CSOs. And that we're building a sort of program investigation so that we can build up that sort of event-based understanding at the catchment scale on the control of pollutants and the contaminant mixtures and how they change with time. So we're using sensors to support that, to provide that high temporal resolution outputs, and so that's only made possible through really using next generation sensors, again, which I'll talk a little bit about in a second. We're coupling these sensors with Scottish Water's smart sensor network within the catchment, within a town of East Calder, where they've implemented 60 sensors to measure depth and flow through the hydraulics of the town, so through the pipe work, and then coupling that with hydraulic modelling, so that we can really understand that the processes occurring within that urban environment. And then we've put in place we're putting in place now flow-through systems upstream and downstream of that catchment, where we are embedding, let's say, sort of next generation sensors along with sort of standard sensors, so that we can couple what we're seeing coming through that urban environment with changes in the sort of complex cocktail of pollutants within the water that we're measuring. And those are also positioned so that we can look at the impact of overland flow and the impacts that's having on water quality from 3 sub-catchments with very different land cover characteristics as well. So work package 2 within this and brings that sort of wealth of national data sets together, so integrating those and integrating data ultimately which is fairly disparate and unaligned to really solve those longer term spatial temporal variations in pollutant exposures, and to assess the combined effects of contaminant and climate and hydrological factors on aquatic ecosystems using more novel data analytics, including AI and data mining and machine learning type technologies. So theme 2 then, here we're really exploiting more on that national data sets to really understand that sensitivity of ecological indicators, including eDNA, to assess the impact of both acute and chronic exposure. So bringing the data sets together from both the catchment and the national scale. And at the national scale, we will explore the impacts of chronic chemical exposure on functionally diverse freshwater biota. Now, traditional approaches in analytics have perhaps focused on time series regressions, usually considering one pollutant at a time. This approach, however, that we're exploiting here, this has been limited by sort of also the mismatching of sampling strategies of ecology and chemistry in these environments. Here, however, we'll be using a sort of transformational data science and analytical techniques, including a suite of geospatial AI methods to create an analytics pipeline suitable for ultimately classifying and quantifying that sort of spatial temporal variation in potential exposure to mixtures of pollutants, determining and modeling the effects of geographic, catchment and hydroclimatic drivers on chronic, mean and acute extreme chemical exposures and their ecological impacts, and developing indicators of sensitivity to chronic and acute chemical exposures by quantifying their impact on ecological receptors. Now, work package 3 then really focuses on bringing this together, and providing a systems-wide approach that delivers on theme 3 of the call, supported by our interdisciplinary team and our proposed use of existing and new data and novel data analytics. And in doing so, we recognize that most models and decision support tools underrepresent the site and catchment specific nature of contaminant loss and are limited by gaps in observational data and knowledge. So we will overcome these limitations by integrating the outputs from work package 1 and 2 within a probabilistic framework that will include hydrological pathways and the effects of contaminant mixtures on that sort of ecological safe space that we're defining. So a decision support tool will be developed to improve the understanding of pollutant risk and the associated uncertainties. And we will co-design and co-develop the decision support tool to inform on current and future conditions and support the implementation of effective interventions, be that through policy or regulation or indeed technological advancement. Now, much of this is possible because it's a very ambitious program, because we're building on existing developments. And one of the key developments that we are benefiting from is the development of this digital observatory, which is the first phase of Scotland's International Environment Centre, which is funded by both UK and Scottish governments through the Stirling and Clackmannanshire City and Region deal. And it's the development of a digital observatory at the full catchment scale, so we can understand a full continuum of water in terms of water quantity and water quality, and how we can manage it more effectively to tackle the challenges that we have around climate extremes and climate change, but also explore the benefits of managing water more effectively, recovering resource, for example, benefiting from carbon sequestration and promoting that in the landscape, and as I said, mitigating these extreme events as well. And that also includes some engagement with urban environments, greening up those urban environments, promoting biodiversity opportunities, and that collectively helps support thriving communities, but also promotes and enables improved regulation as well. So this then brings together existing data sets. It brings together sort of this about 300 sensors around water quality and water quantity, including high resolution rainfall radar, and also brings together our satellite monitoring capability in terms of water quality that we've been pioneering for many years now at the global scale and bringing this down to the local scale, and also in water quantity in terms of soil moisture and flooding as well. Now, I don't have much more time to go into that in much detail, but just to maybe emphasize some of the sort of research and innovation that both the Hydronation Chair program, which I lead, I mentioned at the start, and the Mot4Rivers program that I just described is enabling. So as I mentioned, we developed this capability of using satellites to monitor water quality at the global scale. But now with the next generation of satellites, we can go beyond looking at large targets like large lakes and actually begin to start observing river systems for the first time. And this is a project that we're doing with Dow in the States to understand how large chemicals industries having impacts on both their own assets and also the river system as well. And this is sort of technology that we'll be bringing into play here, particularly within the Arm catchment and the wider Forth, especially. We're also working with Satellite View, which is a startup company funded by UK and European space agencies who are about to launch a series of satellites that will present an unprecedented capability for us to look at the sort of thermal properties of our environment, and in this case in particular, looking at water mixing, but also identifying CSO discharges into our river environments, and even indeed quite small river environments. So we did a trial flight of the sensor last year, as you can see here, so we can actually image quite a lot, quite a significant proportion of what is actually quite a small water body, as well as identifying heat recovery resources as well. But this is really transformational, because these satellites, the first one of which will be launched in June, will provide 3-meter resolution, and ultimately with the 7 satellites in constellation, 12 times a day, which will really transform our understanding of processes occurring at that spatial scale within the environment. We're also working with fairly new sensor manufacturing companies, many of them spin-out companies, and this is just a couple of examples that I want to highlight with you. And these will be deployed within the Arm catchment, so we can begin to understand these complex cocktails of pollutants through our flow-through systems. And the first one is a spin-out from St Andrews University, light water sensors, and they're developing a sort of photonic-based technology to actually start measuring a whole range of pollutants that were hitherto really challenging to do through in situ technologies, and that includes measuring pesticides and pharmaceuticals. And for example, if we're measuring ibuprofen or indeed caffeine in particular is a marker, then coupling that alongside other measures, for example, measures of coliform, then we can begin to provenance where those pollutants are coming from. So high caffeine, high coliform wastewater treatment works, low caffeine, high coliform concentrations, then that's most certainly coming from overland flow from farmland, for example. And then we're also working with another company, Southwest Sensors, a spin out from Southampton University, and they're developing a sort of lab and a chip type technologies for measuring nitrite, nitrate, ammonia, and orthophosphate in their sensors at a fraction of a cost from current commercially available sensors in particular. So that again will give us that high temporal resolution understanding of the variation in nutrient concentrations with events that are occurring within the almond catchment in particular. So that just gives you a quick flavour of sort of the latest and next generation technologies that we're bringing into this program, so that we can really build new insights into that interrelationship between sort of hydroclimatic streams and that increasingly complex cocktail of pollutants impacting on our aquatic environments and the ecosystems they're in. And this is just a table which is sort of summarising the data sets that we're bringing together for the national scale understanding and modelling that we're doing there, bringing together hydroclimatic catchment data, data on contaminants as well, and other water quality indicators, as well as measures of biodiversity, and that's part of work package 2 and 3 in particular. So I think I'll probably run out of time, but just to say that we have a keen and engaged set of stakeholders, some of which are on the call, but many of which aren't, in terms of the sort of organisations that we've reached out to. Acquia clearly is known to you all, but Scottish Water, a very key partner here as well. But we're also working very closely, and I sit on the advisory board for the UK Water Partnership, working with local authorities as well, so East Lothian Council, as well as obviously DEFRA and Scottish Government. And then obviously we have a series of digital partners contributing to this programme, as well as sort of statutory partners too. And this programme also leads and reaches out to obviously other initiatives around that sort of hydrogenation programme within Scotland, but also we have a number of European projects and intergovernmental panels that we sit on that also benefit from the outputs from this project. So we have focused the funding from NERC very much on that PDRA time and staff time, but we've also leveraged another £650,000 of input, in-kind input, as well as in-cash input. For example, Scottish Water are contributing to the development of those flow-through systems and purchase of sensors for the almond catchment in particular. So we're very much at the start of the programme. It's a 42-month programme, slightly shorter than the others, I think. We have a 6-month startup period where we are obviously recruiting postdocs, but also doing the engineering work and sampling design for the almond and collating those national data sets together. And so I think in future meetings, you'll probably see this diagram and the timeline moving as we move forward. So that's it. I think hopefully that gives you a reasonable summary of what we're trying to achieve. It's certainly quite diverse in terms of the expertise that we're bringing to bear to really shed light on the challenges that we have around water quality and the impacts that's having on ecosystems. So I'll stop there.